Okay, so literal equations is, it's a little weird because you're like solving, but you're not completely solving. You're using, we usually use literal equations when it comes to like in real life. So like for physics, if equations that have to do with like electricity, amps, voltage, those kinds of things, or even in architecture or construction, they're going to be using carpentry, things like that. They'll use a lot of literal equations, and it's basically when you use letters to stand for constants. So constants would be, like things like Avogadro's number in chemistry, or Planck's constant, or things like that, like, because those numbers are usually like 6.023333 times 10 to the negative 23rd. It's like ridiculous, and it's just easier to just keep using the letters, using P or whatever, or A for Avogadro's number, stuff like that. So you're just going to keep those letters as stand-ins. So yeah, really common physics, chemistry, graphing data, things like that. And so our answer, or sometimes we just use it to reword equations so that we can have a formula. You can actually have a formula in like written in multiple different ways. So you can rewrite the area formula in a ton of different ways, right? Right, you're not gonna solve it as in like x equals a number. It's more you're gonna solve for a constant or a variable. And this will make more sense when I just do examples. It's like a weird concept to think about. Okay, so let's say I have 3x plus y. So this is actually really important because you are going to use this a lot for graphing. Okay, you have, in graphing, we're going to work with equations with an x and a y. We'll get to that in 3 weeks. We'll do graphing. And you're going to have to solve for y. Okay, so you might have this, and the problem might say solve for y. So that means I want to end up with y equals something. But I'm not going to have y equals a number. It's going to be y equals an equation. Okay, not a number. That's why it's called like a literal equation, because it's still an equation. You're not like solving for a number. I know it's like really weird terminology, but so we have this, and I want to solve for y. So that means I want to end up with y alone. So I want to get rid of this 3x. Okay, so I need to get rid of it on this side, which means I have to subtract 3x on the other side. But if you notice, 44 and 3x are not like terms. So the best I can do is just keep it as 44 minus 3x. And that is literally how you do it. So I just solved for y, but again, I'm not getting a number, I'm getting an equation. Okay, but you're still doing the same things. You're still transforming just like you would, just like how you would solve for x. It's just know your answer won't be a number. It will be an equation. Okay, so that's another one. And sorry, this one says solve for x. So this time they want me to solve for x. So that means I want to get rid of the 3y. Okay, so I get 0 there. 12 minus 3y on this side. But I want to solve for x, not for 2x, right? I want to end up with x equals something. So I need to get rid of the 2. So I'm going to divide both sides. It's a little tricky one because it's the whole right side needs to be divided by 2. And you can just keep it that way. Unless you know how to like simplify that more, that's fine. But otherwise, this is completely acceptable for me for now. We solved for x. It's an equal, whoa, I don't know what happened there. Equation, and that's good enough for me. Oop, I don't know what it's doing, sorry. And so an example of like, I said you can rewrite equations. So I can rewrite a equals L times y. I can solve for L. So if I want to solve for L, right, I can divide by W, and I get A equals L. Or I could even solve for W. Right? I'm gonna start again. So I'm gonna divide by L. That equals 1. A over L equals W. So I solved for W. Right, so I've written the area equation 3 different ways. Area equals length times width. Length equals area divided by width. Width equals area divided by length. Right, this is the same equation written 3 ways, but where I solve for each corresponding variable. Okay, and that actually comes in real handy. I'm trying to remember. I think I can't remember the, like, electricians. I think this is the equation. I might be wrong. Voltage equals current times resistance, something like that. But they because it kind of depends on like the voltage running through, or you're gonna, maybe you know like the resistance of a light bulb and you don't know the voltage and you need to test things out, right? So it actually helps to know all of these different formulas or have it written in all these different ways. And I might have the formula wrong, so don't take this formula to heart, but you know, like having it in different ways so that whenever you're taking measurements and you're trying to make sure the house is safe electric wise and all this kind of stuff, trying to measure like what kind of wattage and all that, whatever things, you can just plug in like, oh, I need to know voltage, I know amps, and I know resistance, I'm going to plug that in. Oh, I don't know the current, so I'll plug in the voltage, I'll plug in the resistance, that'll give me the current, right? So rewriting it in all these different ways is actually really useful when you're trying to figure out different things, because sometimes you'll know the voltage, you know, and the resistance, and you won't know current. Sometimes you'll know the voltage and current, and you won't know resistance. You know, it just depends on what you know based on the context of the situation. So having it rewritten, solving for them, you know, called literal equations, comes in handy. So that's just something to know, and you're going to use it a lot when we graph. You're going to be solving for y mainly. That's kind of like the big one. Okay, but we'll also use it for like distance and rate time.